Question: why do my veins look blue if my blood is red? Answer: well, let's start with some background. Your body, it does stuff. But to do stuff, your cells need energy. And to get energy from food, they need oxygen. So, when you take a deep breath of fresh air, it travels down to your lungs and dissolves into your bloodstream. However, remember, each cell needs differing amounts of oxygen depending on the liveliness of their previous activities. Thus, while a small part of the oxygen remains in the blood plasma, it needs to be transported in a more sophisticated medium that caters directly to each cell. This medium is a protein called hemoglobin, which makes up over a third of mass of your red blood cells. Question: yes, me, over here. Thank you. In which way do hemoglobin specialize oxygen delivery? Answer: let's go back to the beginning. You breathe in, oxygen rushes down through the branches of your lungs, dissolves into the bloodstream, enters a red blood cell, and what does it do? What? It bumps into hemoglobin. Awkward? A bit. But hemoglobin is actually really cool about it because it's special, and it's special in two ways. First, it is a complex, or group of 4 individual hemoglobin units bound together by intermolecular bonds. Second, and more importantly, each subunit hemoglobin can bind a heme group onto itself. A heme group is a chemical ring that locks an iron ion in its center. The iron ion can bind to 6 ligands, 6 charged atoms that can donate their electrons in order to form a bond. Heme's iron binds to 4 nitrogens in the heme ring, which hold it tightly in place, to 1 nitrogen atom from the hemoglobin to connect it to the protein unit, and the remaining vacancy is left to bind with oxygen. When this last iron-oxygen bond is formed, the iron is pushed deeper into the ring, changing the shape of the heme group. Because hemoglobin is packed so tightly, the heme's change causes a change in the structure of the respective subunit, which in turn changes adjacent subunits, which themselves change their own heme groups, a domino effect on the atomic level. The change induced in other heme groups makes it easier for them to bind to oxygen themselves, so we refer to hemoglobin as having cooperative binding. And of course, once oxygen is bound to the hemoglobin, it needs to be released into hungry tissues. Hemoglobin can be in a tense or relaxed state. The relaxed state binds tightly to oxygen molecules, but increases in carbon dioxide concentration, a byproduct of consuming oxygen for energy, favor the tense state of hemoglobin, which has a lower affinity for oxygen. This is the result of carbon dioxide competing with oxygen for binding with heme, as well as the result of carbon dioxide reacting with water in red blood cells and releasing protons that can also compete with oxygen for binding with heme. This regulation of oxygen affinity allows hemoglobin to deliver oxygen efficiently to the different tissues that need it, as determined by their carbon dioxide levels. Question: well, I'm mind-blown that a few random atoms can organize themselves to do all this. What does any of it have to do with the color of blood? Answer: I am glad you asked. Your veins carry blood back to the lungs after it has passed by the tissues that needed nutrients. These had high carbon dioxide levels, so heme groups lost their oxygen, which happened to take an electron from iron along with it. Electrons around an atomic nucleus are arranged in different orbitals, or areas they can occupy around the nucleus. Some electrons have more energy than others, and the more energy they have, the greater the energetic state of their orbital. These differently energetic orbitals can hold varying amounts of electrons. When an electron is removed from the heme group, a lower energy electron can move up into the highest energy orbital surrounding its nucleus. But this requires energy. Where does it get that energy from? Light. When rays of light strike the electron, it can absorb part of the energy being transmitted by that light and move up into a more energetical orbital. Light is the mixture of many electromagnetic wavelengths, each representing a color. The iron atom in deoxygenated hemoglobin only absorbs energy from light with wavelength 660 nanometers. This is the color red, which is then removed from the mixture, leaving behind only blues and greens, the colors that combine to give your veins that veiny color.